I decided to make a video where you can watch me as I make my solution key to this Advanced Functions Grade 12 test I give in the Trig Identities and Equations unit. There's 4 multiple choice questions to start. Number 1, which of the following is equivalent to sine 3 pi over 4 times cos pi over 3 plus cos 3 over pi over 4 times sine pi over 3. I noticed this follows the compound angle identity for sine. In the compound angle identity for sine, if these two angles match, like in the identity, and if these two angles match, like in the identity, I know I can rewrite it as sine of those two angles added together. So in this question, it would be sine of 3 pi over 4 plus pi over 3. You can quickly get a common denominator there, and I could see that that would equal sine of 13 pi over 12, which is option A. Number 2, which of the following is equivalent to 2 times sine of 4x times cos of 4x? That follows the double angle identity for sine. I've got 2 times sine of an angle times cosine of the same angle. Whatever that same angle is in these two spots, we can rewrite it as sine of 2 times that angle. So in this question, it would be sine of 2 times 4x. And 2 times 4x is just 8x. So my answer for number 2 is C. Number 3, I notice answers A, B, and C are all double angle identities for cosine. I'll just jot those down on the side here for you. Those are the 3 versions of the double angle identities for cos. So let me rewrite the original question. Let me rewrite the angle as a double angle. So this would equal cosine of 2 times 3x. So 3x is the angle being doubled. So if I change, I notice in the second identity I wrote, if I change that x to a 3x, I notice I would have answer B right there. Number 4, which of these is a possible solution for cos squared plus sine squared equals 1 on the interval between 0 and 2 pi? Well, this right here is the Pythagorean identity. Because it's an identity, we know it's true for all values of the variable. You could plug in anything you want for x, and the equation will be true. So A would be true, B would be true, and C would be true, meaning the correct answer to this question is D. The next question is where we start proving some trig identities. It says prove 2 of the following identities on this page, show all of your work. Let me start with part A, and I will separate it into left side, right side. The first thing I'm going to do with this one, on the left side, I am going to factor the numerator and the denominator. The numerator is a difference of squares, so it factors to cos x minus sine x times cos x plus sine x. And in the denominator, I notice the first term and the second term both have a factor of cos x that I could common factor out. So I will divide out a cos x from the first and second term. When I divide cos squared x by cos x, I get cos x. When I divide sine x cos x by cos x, I get sine x. And then I see in the numerator and denominator, I have a factor of cos x plus sine x that can be canceled with each other, which leaves me with cos x minus sine x all over cos x. Now I could go to the right side and make it look like this, but I think I'll just continue on the left side here. The cos x and the sine x are both being divided by cos x, so I'm going to separate this fraction into 2 fractions. And I have cos x over cos x, which is 1, and sine x over cos x, which is tan x. There's that identity proven. We can say left side equals right side. Now let me just move this off to the side. And let's do another one. Let's do part B. Let me separate left side, right side quickly. Notice on the left side, I rewrote the binomial squared as sine x plus cos x times another sine x plus cos x, so that you can see when you expand this out, you would get sine squared x plus 2 sine x cos x plus cos squared x. And then if I rewrite this with the sine squared x and the cos squared x beside each other, it'll be obvious what we do next. Right here, I've got the Pythagorean identity. Sine squared plus cos squared is always equal to 1. So this equals 1 plus 2 sine x cos x And 2 times sine x cos x is the double angle identity for sine, so I could rewrite that as sine of 2x, which is exactly what I have on the right side. So I can say left side equals right side, and that identity is proven. Let me shrink that one and move that one out of the way as well. And then lastly, we have part C. Let me rewrite that. Okay, what am I going to do here? On the left side, I'm going to do a couple things to simplify this. I'm going to take this cosecant of 2x. I can move it to the denominator if I rewrite it as sine of 2x, and I can take this secant x, move it to the numerator if I rewrite it as cos x. I could rewrite that tan x as sine x over cos x. And that sine of 2x, I'll use the double angle identity. That is 2 sine x cos x. What can I simplify here? I have a factor of cos x that cancels with that. I've got a factor of 2 that cancels there. And I have this factor of sine which cancels here. So everything in the numerator canceled, which means I'm left just with a factor of 1 up there. In the denominator, I have a cos x. Notice, that's exactly what I have on the right side. Secant is 1 over cos x. So I've proven the left side equals the right side. That one's an identity. Let's move on to the next question on the test. Use an appropriate compound angle formula to find the exact value of sine of 13 pi over 12. Show all of my work, proving I can evaluate without a calculator. For this question, I'm going to need to remember my special triangles. So let me just redraw them on the side here quickly. Okay, I've got them drawn there. If I want to find the exact value of sine of 13 pi over 12, I'm going to have to rewrite the 13 pi over 12 as a compound angle, so as a sum or difference of angles, that I'm able to use my special triangles to help me get the exact values of. So I am going to rewrite 13 pi over 12 as 9 pi over 12 plus 4 pi over 12. The reason why I know those would be good angles to break it into is because both of those reduce to 3 pi over 4 and pi over 3. And I notice that both of those angles I reduced to would have their reference angles that are in the special triangles. I could use my compound angle identity for sine that tells me that sine of the sum of two angles equals sine of the first angle times cos of the second angle plus cos of the first angle times sine of the second angle. And then sine of 3 pi over 4, I know is going to be equivalent to sine of its reference angle because it's in quadrant 2. But cosine of 3 pi over 4 is going to be equivalent to negative cosine of its reference angle because cosine is negative in quadrant 2. And now I can just go ahead and replace each of those four ratios with what my special triangle tells me it's equal to. Sine of pi over 4 is 1 over root 2, which I could rationalize to root 2 over 2. Cos of pi over 3 is a half, minus cos of pi over 4 is root 2 over 2, and sine of pi over 3 is root 3 over 2. When I simplify this, I've got root 2 over 4 minus root 6 over 4. It's a common denominator, so we can write this as a single fraction, root 2 minus root 6 all over 4. Number 7, angle x and y are both in the fourth quadrant, such that sine x is negative 3 over 5 and cos y is 5 over 12. Let me start by drawing where those angles would fall on a Cartesian grid. And now let me draw angle x, which I know is in quadrant 4. And what ratio do I know for x? I know sine x is negative 3 over 5. So I know from my reference angle, I know sine would be opposite 3 over hypotenuse 5. And it's negative because we are in quadrant 4, where of course the sine ratio is negative. If I use Pythagorean theorem, I could solve for the third side of this right triangle and I would get 4. Now if I wanted to get any ratio for angle x, I could use its reference angle as long as I check cast rule. How about angle y? Well, it's also in the fourth quadrant. And what ratio do we know? We know cosine of y is 5 over 12, so adjacent over hypotenuse is 5 over 12. If I use Pythagorean theorem, I would solve for the length of this side to be the square root of 119. And I could get any ratio I want for angle y, which is this angle here. by using the reference angle and the castrol. So let's go ahead and see what we need to find here. We need to find sine of x plus y. We don't actually need to solve for x or y, we just have to figure out what is sine of x plus y. So I can use the compound angle identity, sine of x plus y equals sine x cos y plus cos x sine y. And then if I look at my two diagrams, I can get any ratios I want. Sine of x is negative 3 over 5. Cos of y, I have to look down at my second diagram. Cosine of y is adjacent over hypotenuse, 5 over 12, and it's positive because in quadrant 4, cosine is positive. Cosine of x, if I look at angle x, cosine adjacent over hypotenuse is 4 over 5, and I can leave it positive. Sine of y would be opposite over hypotenuse, but I have to make it negative because in quadrant 4, sine is negative. And if we simplify this, we get negative 15 minus 4 root 119 all over 5 times 12, which is 60. How about an exact value for tan of 2x? Well, the identity for tan of 2x is 2 times tan x over 1 minus tan squared x. So I just need to look at my diagram with angle x, and tan is opposite over adjacent, 3 over 4. But because in this quadrant only cosine is positive, I know it's going to be equal to negative 3 over 4. So let me replace each of those tan x's with negative 3 over 4. So I have 2 times negative 3 over 4 all over 1 minus negative 3 over 4 squared. And we just have to go ahead and simplify this. I get negative 6 over 4 over 1 minus 9 over 16. Let me keep simplifying over here. Negative 6 over 4 is negative 3 over 2. That's all over. 1 minus 9 over 16 is 7 over 16. I can flip and multiply, so negative 3 over 2 times 16 over 7. 16 divided by 2 is 8. So my final answer is going to be negative 24 over 7. And then the last section of this test, we're going to solve a few trig equations. And the question tells us specifically only find the answers between 0 and 2 pi. And if we have to, round to the nearest hundredth of a radian, so 2 decimal places, but give exact answers where possible. Let me just really quickly redraw those special triangles here, because we might need those for the exact answers. For part A, we should always start by isolating the trig ratio. So I will isolate the tan x by moving the 1 to the other side. I have tan x equals negative 1. I like to always then draw my Cartesian grid and figure out where my answers are going to be. For this question, because I have a negative tan ratio, I know my answers are going to be in quadrant 2 and 4. So I will draw a terminal arm in both of those quadrants. And I know both of those principal angles are going to have the exact same reference angle. So I'm just going to label both of them with the same reference angle beta. And then I check and see, can I get that reference angle from my special triangle? Can I get a tan ratio of 1 from a special triangle? Yes. Opposite over adjacent from pi over 4 would be 1 over 1. So if I place pi over 4 as the reference angle in both of these quadrants, I can figure out my two principal angles. My first angle, x1, I notice that I am pi over 4 short of going pi. So I could say x1 is pi minus pi over 4, which is 3 pi over 4. So that's one solution, 3 pi over 4. And my second answer, I need to figure out how far do I have to rotate to get all the way to here. Well, I'm pi over 4 short of going a full 2 pi. So x2 would be 2 pi minus pi over 4. And that would give me 7 pi over 4. So my second answer, 7 pi over 4. And don't forget, you can check both of those answers. Plug them into the original equation. Make sure that tan of both of those plus 1 is equal to 0. Part B. This time I have secant x equals 7 over 4 once I rearrange that. And I'm going to change this to a primary ratio. If secant x is 7 over 4, then I know cosine x is the reciprocal of that, which is 4 over 7. I'll draw my Cartesian grid quickly. And because for this question I have a positive cosine ratio, I know my answers are going to be in quadrant 1 and 4. So I will draw a terminal arm in both of those quadrants. And I know both of those angles have the same reference angle. I can't make a ratio of 4/7 from either of those special triangles, so I have to ask my calculator for the first answer by doing inverse cos of 4/7. So I'd say x1 is inverse cosine of 4/7, and that is about 0.96. In quadrant 1, if the answer is 0.96, that's also the reference angle. So I know the reference angle in quadrant 4 is also 0.96, and I can get that angle number 2. I notice that it is 0.96 short of 2 pi, so I'll do 2 pi minus 0.96. It gives me about 5.32. So x2, 5.32. If I check both of these answers in the original equation, it might not make it equal 0 exactly, but it should be very close. Keep in mind these are approximate answers. We rounded those two final answers. Part C, I have sine squared x equals 3/4. Well, I want to take care of that squared by moving it to the other side. The inverse of squaring is plus or minus square rooting. And the square root of 3, nothing I can do other than write root 3, but the square root of 4 is 2. So I have sine x equals plus or minus root 3/2. Let me draw my Cartesian grid. Now, because I want positive root 3/2 and negative root 3/2 for sine ratios, I know I'm going to get an answer in all 4 quadrants. Quadrant 1 and 2 for the ratio of positive root 3/2, quadrant 3 and 4 for the ratio of negative root 3/2. So I will place terminal arms in all 4 of those quadrants. And the great thing about this question is that all 4 of these are going to have the exact same reference angle. Now, can I get that reference angle from my special triangle? Can I make a sine ratio of root 3/2 from a special triangle? Yes. Sine of pi/3 is root 3/2. So I'll place pi/3 as the reference angle in all 4 of those quadrants. I won't write it in all of them. You can see that there's beta in all of them. So I can get all 4 of my answers. My first answer is just pi/3. My second answer would be pi minus pi/3, which is 2 pi/3. My third answer is past pi by pi/3, so that's 4 pi/3. And my last answer, x4, is pi/3 less than 2 pi, so 2 pi minus pi/3, which would give me 5 pi/3. So I'll list all of my answers in the solution box. Pi/3, 2 pi/3, 4 pi/3, and 5 pi/3. Because these are exact answers, we could check all of those in the original equation, and it should make it work out exactly. My last question is a quadratic trig equation where I'm going to have to factor this. I notice I'm going to have to find numbers that have a product of a times c, so a product of 2 times -1. So multiplies to -2. And a sum of the b value, which is -1. The numbers that work are -2 and 1. So I split the middle term into -2 cos x plus 1 cos x. Now I factor by grouping. The first 2 terms I take out a 2 cos x, and I get cos x minus 1. The last 2 terms I take out a 1, and again I get cos x minus 1. So I have the common binomial of cos x minus 1. And my second factor is 2 cos x plus 1. And now I have to solve when are each of these factors equal to 0. So when is cos x minus 1 equal to 0? And when is 2 cos x plus 1 equal to 0? Well, cos x being equal to 1, I can think of the unit circle. Let me just quickly draw my Cartesian grid. I know that the cosine ratio is equal to the x-coordinate of where this terminal arm intersects the unit circle. So where can I rotate to get the x-coordinate to be 1 if this is a unit circle? And that would be to right here. Right, this point right here is the point 1, 0. So if you rotate 0 radians or 2 pi radians, you get a cosine ratio of 1. So I have 2 answers to start with. Is 0, x2 is 2 pi. So I've got 0 and 2 pi. And then let's see if we can get any answers from the second factor being 0. When is 2 cos x plus 1 equal to 0? Well, that would be 0 if cos x was equal to negative 1 over 2. And I'll draw another Cartesian grid. This time I have a negative cosine ratio. Cosine is negative in these two quadrants. So I will draw a terminal arm in both of these quadrants. I'll call this my third and fourth answer. I know both of these answers have the same reference angle. And can I make that reference angle from a special triangle? Yes, cosine of pi over 3 is a half. So I'll place pi over 3 in both of those quadrants. And I'll get a third answer of pi minus pi over 3, which is 2 pi over 3. And a fourth answer as pi plus pi over 3, which is 4 pi over 3. So I'll add those answers. And there we go. That question's done. One question left. Solve for when sine of 2 times an angle equals negative root 3 over 2. Often for this question, I'll say let k equal 2x, and then I'll just solve that equation for k, and then resub back in the 2x for k. So I have sine of k equals negative root 3 over 2. Sine is negative in quadrant 3 and 4, so it'll be an answer for k in both of those quadrants. I can make a ratio of root 3 over 2 from my special triangle. Sine of pi over 3 is root 3 over 2. Seem to be using pi over 3 a lot. So I'll place pi over 3 as the reference angle in those two quadrants, and I'll get two answers for k. My first one, I have that as 2 pi minus pi over 3, which is 5 pi over 3. And my second one as pi plus pi over 3, which is 4 pi over 3. Remember, each of those k's is actually 2x. We'll isolate the x in both of those by dividing the 2. Gives me 5 pi over 6 and 4 pi over 6. I can simplify that one to 2 pi over 3. Now for this question, sine of 2x will complete 2 full cycles between 0 and 2 pi. So these are the answers in the first cycle. To get the answers in the second cycle, I'm going to add the period of sine of 2x, which is pi, to both of these answers. So my third answer, I'll just add pi to 5 pi over 6. 5 pi over 6 plus 6 pi over 6 is 11 pi over 6. And my fourth answer, I'll take my second answer, 2 pi over 3, and do the same thing. Add pi to that, which gives me 5 pi over 3. Those are my answers in the second cycle of sine of 2x. So I have 4 answers to this equation. I have 5 pi over 6, 2 pi over 3, 11 pi over 6, and 5 pi over 3. There's all 4 answers to that equation. There's the end of the test. Jensen Math.